now we will do what we did last time was we did the small signal analysis of the differential pair, right? And we showed how to find the gain. In one case, it becomes the common emitter with emitter degeneration. So remember, we did the small signal analysis. Small signal analysis. Okay, how did we do it? We for a differential mode analysis. Okay, in a differential amplifier, there are two kinds of signals. I'll again reiterate that, but let us consider this one. Okay, so what we did is, so we did two kind of, so this is the tail, I tail. Okay, and sometimes it is also called ISS, IEE, because it is connected to the emitter, and in case of a MOSFET, it is called ISS. So we did the analysis for V in here, where we apply an input signal and we take the differential over here, so RC and RC, and we take the difference over here, V out. And we did the analysis by saying that, okay, from input to output, what is this point to this point? So let's call this as VO1, and this side is VO2, and V out equal to VO1 minus VO2. Okay, so what we did is we found the gain from here to this point, VO1. How did we find it? So this becomes Q1 degenerated with Q2. The resistance of Q2 is 1 over Gm looking into the emitter. So it becomes a Q1 is a degenerated transistor, emitter degenerated transistor, degenerated by the emitter resistance of 1 over Gm2 of Q2. Okay, and we found this. Then we found the gain from input to this node. And how did we find? We found it by this becomes a common base topology. And in order to do that, we found out what is the Thevenin voltage and Thevenin resistance looking into this node. We solved it. So in order to find the Thevenin voltage, we said that this acts like an emitter follower. So V in equal to here, whatever V Thevenin equal to V in. And we found out the resistance looking into this, which is nothing but 1 over Gm1, and that became the R Thevenin. And thereby, we found the gain from the input to this output, and then we took the difference and divided that by the gain, divided that by the input to obtain the overall gain of the circuit. Okay. Then we said that, okay, we are applying an input signal, so the input signal is not fully differential. So what if we apply a fully differential signal? Okay. So fully differential signal, we do this. So it is RC, RC. Okay. So that means now the fully differential signal will be denoted as V in P, and this side it will be denoted as V in N. And we do have this IEE. We'll define this as VON because in P output will be negative, and therefore this is in N VOP. So we will have V out equal to VOP minus VON, and V in as V in P minus V in N. Okay, therefore the voltage gain is going to be V out over V in. Now, in order to do that, the observation that we make is that V in P and V in N are differential signals. So when I say they are differential signal, what it means is that when V in P goes out around the common mode, so there is a V input common mode, V input common mode, then the output, the inputs V in P, this is V in P, then this is going to be just opposite in phase and exact amplitude of swing. This is going to be V in N. So we are going to apply V in P and V in N over here. And when we do that, what we see is that this node voltage doesn't change at all. If this increases by a certain amount, this decreases by the same amount. This node voltage does not change at all. Okay, it is like a pivot in a seesaw. It is swinging around that. So therefore, I can consider this as if this node is not swinging, what is this? This becomes an AC ground. Okay, this is an AC ground. So therefore, I can say that this becomes this thing, we replace it with its half circuit. So we replace this with its half circuit. Okay, and the half circuit is going to look something like this. V in P slash N for both sides, and this is going to be VON slash VOP. Okay, so half circuit, I find the gain from each side to the output, and this is nothing but a common emitter amplifier. Okay, and that is how we found it. So what we said here is that this signal, so the input is going to swing. Now the input can have two different swings. Okay, one is the differential swing. When there is a differential swing and I monitor the differential output, we call that as the differential gain. So this becomes differential gain. Differential gain. Okay, this is called the differential gain. Differential input, differential output divided by the differential input. But there is another thing that can also change. What is that? That is the common mode. The common mode, the input, differential input is not changing. Differential input is fixed. But the common mode, that means both of them can move up and down together. Input side. If both of them move up and down together, then this output is also going to move up and down together. Okay, so we will now do the small common mode gain analysis. Common mode gain analysis. So when we do the common mode, what did we say? That both the terminals, the common mode input moves up and down together. So IE over here and RC. Now this thing connected here. So both of them move together up and down. Okay. So V in CM. So V in CM is going to move up and down together. Then automatically this node, if this goes up, this goes down. If this goes up by an X amount and this goes up by the same amount, then both of them. So I can virtually short both of them. Okay, so both of them, the output will V out will move up and down together. Okay, so therefore this circuit boils down to a circuit which is going to be RC by 2 and these two transistors connected in parallel, and there is an IEE here. So I can do like this, V in CM, then what happens? V out CM. So V out CM divided by V in CM is called AVCM, common mode gain. So this common mode gain is going to be, therefore, what is the common mode gain in this circuit? Anybody by looking at this circuit? Rishabh Sonkar? Rishabh?
Yeah, sir.
So what is the common mode gain if for this circuit what I have drawn?
Sir, I have to calculate this.
By looking at it, can you say anything? Harsh?
GMRC by 2.
Shubhayan, Mohammad Arif Hussain, right? What is your thought?
Yes, sir. So something similar to that what Harsh said. GMRC by 2.
I like your
maybe.
jacket. You have a split jacket you're wearing in your this thing, purple
Yes.
on the right.
Yeah, that's lighting. Different
And
lights on two different sides.
I see. Okay. 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 The Lamborghini guy, Lamborghini and Ferrari, Harsh Agarwal.
It's a GMRC.
GMRC by 2.
It's a wanted to be GMRC that because it's 2 GM. So those two are in parallel.
Those two are in parallel. That is a good point. So this is GM and GM. So it becomes 2 GM. That I fully agree. अभी तक कोई समझा नहीं है this thing. Very sad. right? If I change this voltage, the gain comes due to the change in current. Can the current in this circuit change? Can the current in this circuit change? Anyone? Subhayan? Sai Ram Reddy?
Sir, if there is no RO, then
No. Can the, if suppose there is RO in this also, let there be RO. Can the current through this circuit change?
So since we are giving a constant current source, I don't think the current can change as a whole.
Then what will be the gain? What will be the gain?
0.
0. So the common mode gain of this circuit is going to be 0. You cannot change the current flowing through this circuit. So the thing is, if I have an ideal tail current source, I get a good differential gain because differentially this node doesn't move, so this stays constant. So the current is going to circulate here in this loop. Okay, because it is going one side current will increase, other side current is going to decrease. So that is possible. Okay, but in this scenario, both of them are connected together. The outputs are shorted in a way, virtually shorted. We can say that they are virtually short. This short is a virtual short. Keep this in mind. This is a virtual short. When is something a virtual short? When both the nodes move together at the same time, then it's a virtual short. Okay. So am I clear? So this gain is 0. So that means now if I have a tail current, a current source with certain resistance Re, can you tell me what will be the common mode gain then? It becomes this combined transistor being degenerated by this emitter resistance, this resistance, which is a current source resistance, and that so it is degenerated resistance times RC by 2. That will be the, so it is therefore AVCM equal to twice GM divided by 1 plus twice GM RE times RC by 2. Okay, so this is going to be the, so that is the reason why we go for very high output impedance in the tail current. That is the reason why we design current sources to be a very, that is one application. If the current source resistance output impedance is very, very large, then the common mode gain keeps reducing. So this will be roughly equal to RC by RE. Now, if RE tends to infinity, then AVCM tends to 0. So a good differential amplifier, good diff amp. So this one AVCM is the common mode gain, and this gain is called AV diff. Okay. So a good differential amplifier has AV diff tending to infinity and AVCM tending to 0. Now you can appreciate why you had to design current sources with very large output impedance. Okay, if you make these current sources with very high output impedance, then it behaves more like an ideal differential amplifier, by amplifying the differential signal and rejecting the common mode signal. And this is very, very important because the common mode signal could be bouncing around because if there is noise in the system. Okay, so you want to get rid of that common mode signal. So the differential amplifier does it nicely for you. So you have to make sure that that doesn't happen. Now, to find the differential gain for this course, we can find the differential gain using the concept of half circuit. Obtain differential gain using concept of half circuit. Okay, this is a concept of half circuit. That means you find out which node exactly, at which point, which node is an AC ground in the half circuit. So in this case, the AC ground. And in the previous class, I had given you one topology where I did something like an amplifier here. So IEE by 2, and this is IEE by 2, and I told you what is the differential gain of this, right? RC, VON, VOP, V in N. So I had asked you, this is REE. RC. So this is RE. Now, what is AV diff here? AV diff. In order to obtain the AV diff, you have to draw the half circuit of this. The half circuit of this is going to be, you find out which node doesn't move. Exactly at the center point here, if this goes up, this node is not going to move. Okay, if this goes up, this goes down, the center point. So the half circuit of that is going to be RC, then this thing, and RE by 2. This is going to be your half circuit. Am I clear? Any questions on this? Hello? Sorry, I cannot hear you.
Hello.
Yes.
Sir, the V in common mode was a DC signal, right? Means
It is
it was a DC.
yes, but it can
So
change,
how
right? It can change.
slight variation, like you said.
Yeah, it changes because. So how do we generate a DC? So actual signal in the world is single-ended V in. We pass it. So if I have to convert it into differential with a certain common mode, I apply a battery here, right? V in P, correct? Now
Yes, sir.
this battery voltage would be changing as a function of time. Can be changing slowly, right? But it
Yes,
will be
sir.
changing as a function of time. So that means there will be, if this changes, the common mode changes, then the output common mode will keep on changing. So change in the output common mode divided by the change in the input common mode is actually the gain. Ideally, I should put a del here, but I ignored that del and said that, okay, this is the common mode gain. So if I have a very high output impedance, you can change the battery voltage here. Okay, the thing is that the output common mode is going to stay. That means it is rejecting the common mode change very nicely. Am I clear?
Yes, sir.
Any questions? So in this circuit, right? If I have the RE over here. Suppose there is a resistance here, R1, and this has a resistance here, R1. Can anybody solve this? Tell me what is the common mode gain of this circuit? Can you please draw the common mode equivalent circuit of this? Okay, so let me redraw it again. So let us see whether you understood things. So we have an amplifier like this, and unfortunately the current source here is not a good one. It has some resistance R1. Right? So we have this one here, and this one is R1 here. So Q1, Q2, V in common mode. Now the common mode keeps on changing. Can you please tell me what will be the common mode equivalent circuit? Just like the way we got the common mode equivalent circuit of this, like this, putting them in parallel. So what will happen? So RC will, when both of them move up and down, then these two nodes will move up and down together. So these become virtual short. So that means we will have RC by 2. V in CM. Then what happens? What do I do at the bottom?
R1 by 2 parallel.
Sorry? So what should I put here?
So maybe R1 parallel RE by 2.
R1 parallel RE by 2.
I'm not sure.
How about others? Anyone else?
Sir, can we sort the emitter of the two transistors like that? There should be one RE.
Should there be an RE? Think of it this way. If this goes up at the same time because they are shorted. Won't
No,
these
there
two
is
nodes
no-
move up and down at the same? This will move up and down?
At
Yes
the
or no?
same rate. Yes.
Same voltage, so RE vanishes. For a common mode analysis, RE vanishes. So it will just be R1. That's why I had shorted it. By mistake, you should have taken the hint there. So it becomes R1. Am I clear? So that means these two nodes again become virtual shorts when the things move up and down together. Any questions on this? Okay, so I think with this I'll stop the class. I thought I'll do the large signal analysis. So bottom line, let me summarize what we did. There is AV diff obtained by half circuit analysis. Half circuit analysis. So I might give you tricky problems where the half circuit will you have to obtain it in a weird way. AVCM obtained by finding virtual shorts. Virtual shorts. Okay, what is a virtual short? These two are virtual short. That's why I've shorted them. These two become virtual shorts. That's why I've shorted them and you drew. So this is obtained by doing a virtual short. Okay, so these are all small signal analysis. I will discuss large signal analysis tomorrow, and we wrap up the differential amplifier, and we go to feedback on Friday. Any questions?
So why it isn't R1 by 2?
How will it be R1 by 2? Each is independent, right? I have IE here, IE by 2. Why will it be R1 by 2?
Yes, sir, I understood.
No, sorry, made a mistake. It should be R1 by 2. Okay, sorry, thank you. Okay, so with this, I'll stop today's class. So